Okay, so we are going to discuss students' t-distribution. Um, the book has an interesting side note about how it came to be called that. A guy who was working at the Guinness Brewery came up with it and published it, and somehow his employer was involved in that, and they forced him to publish under a pseudonym, so he chose to publish as Student. And it's still called the student's t-distribution instead of the name which I read in that side note and have already forgotten. Um, okay, so the student's t-distribution is a way to get around the not knowing the population standard deviation, basically. Um, so if the population is normally distributed, or we can reasonably assume it is, or if the sample size is large enough, then we can use the student's t-distribution to get the margin of error, even if we don't know the population standard deviation. It's another continuous probability distribution. It is used fairly often. It's very similar to a standard distribution. It's also bell-shaped. It's centered at 0. It has fatter tails, as it says there. It's a little bit squatter, a little bit fatter on the outside. And instead of having two parameters, the mean and the standard deviation, the t-distribution has only one parameter, the number of degrees of freedom. I glanced through things and I did not see where they define degrees of freedom in the text, so I will make sure I do that throughout. It is basically sample size minus 1. So if my sample size is 10, my degrees of freedom is 9. My sample size is 74, my degrees of freedom is 73. Um, so, as with the normal distribution, there are infinite possible t-distributions. It's one for each degree of freedom, though. Your t-distribution is already a standardized distribution in that it's difference from the mean is what it's giving. You're not doing a raw data type thing like it with the normal distribution where you standardize it to get z-scores. The t-distribution gives you t-scores, and there's a different t-distribution for every degree of freedom. Other thing to note is that the t-distribution curve gets closer and closer to the normal distribution curve as your degrees of freedom increase, and it matches the normal curve at infinite degrees of freedom. Okay, so in terms of properties, it's bell-shaped and centered about 0, just like the normal curve. Total area under the curve is equal to 1, just like the normal curve. X-axis is a horizontal asymptote, just like the normal curve. Difference is it is completely defined by the number of degrees of freedom, rather than by the mean standard deviation. As I said, there is no standard t-distribution. Each t-distribution has to be considered individually. In spite of this, we still use tables to look up things related to the t-distribution. We use tables to look up the critical t values. These are just like the critical z values we talked about in the last section. And these critical values corresponds to a given probability value and number of degrees of freedom. So see an example of what the table looks like in the next slide. In general, if you're looking at a table, and let me flip to this one, and the number of degrees of freedom you need is not listed, you go to the next smaller value. So in table C in Appendix A in the book, there on page 884. We've got 1, 2, 3, 4, goes by ones until it gets to 32, and then at 32 it starts skipping till it gets to and does just the evens until it gets to 40, and then it goes 45, 50, 55, 60, 70, 80, 90, 100, 120, 200. So it starts skipping as you go up. But use the next smaller number so you've got a more conservative calculation. Okay, so let's look at a small portion of the degrees of freedom. Sorry, of the t-distribution table. So these are the critical t-values associated with particular areas under the curve. So this is exactly opposite of what the z-value table, the normal distribution tables in table 1, or sorry, A and B in the appendix give. We've got the area, so this would be and you'll have to note we've got area in one table and area in two tables. Believe we get into that tails, not tables. Believe we get into that in a bit. So if we've got a area of 0.1 in one tail and 6 degrees of freedom, then their critical t value is 1.44. So an area of 0.1 in one tail would be a 90% confidence that it's outside of that one tail, right? Hopefully that will become more clear as we go along. So again, as the degrees of freedom increases, the tails become thinner and it gets closer and closer to the normal distribution. At infinite degrees of freedom, it matches. So if you check the table in the book, the last row is for infinite degrees of freedom, and those are the values from the critical z-scores given in the table in the section we just finished. Okay, so the value given in a table is the area to the... Alright, so the t value given in a table matches the alpha value to the right on a one-tailed portion. So if we were... Here's our alpha value across the top here. There's the t value. So if I'm after an alpha of 1 or 10%, that would be that probability there. That's my 10% or 0.1 probability, however I want to think about it. And that's the t value associated with that alpha. So let's look at an example. If we want to find the t value, t sub alpha, t of 0.025 for a t distribution with 25 degrees of freedom. Okay, so 25 degrees of freedom is the first column. We want to find the 0.025 in the one-tailed row and find where those intersect. Right, so it's 0.025. This intersects at 2.06. So our critical t value is 2.06. So there we go. Area in one table of 0.025. Degrees of freedom 25. There's our intersection. Okay. Alright, so we have 17 degrees of freedom, and the area to the right of t is 0.1. So that means our alpha is 0.1 in this. use alpha as 0.1, 17 degrees of freedom. So if we look, we've got 17 degrees of freedom and alpha, and one tail, we've got 1.33. All right, so now if we're looking for the area to the left instead of to the right, the area to the left is 0.05, so alpha will be 0.05. Degrees of freedom is 11. We get 1.796. Remember, this is symmetric, so it doesn't matter if I'm looking off to the left or off to the right, it's going to be the same area. We'll go 0.05, 11, 1.796. Okay, this can right. One gotcha, it's symmetric. Since we're off to the left, though, we are after the negative of that. Right. Because we are after this t here, which is a negative number, because it's less than 0. It's off on that side. So you do have to pay attention to that and adjust the sign to match what you're doing. Apparently only some TI-84 plus Silver Edition calculators can do this. I know it's possible in Excel. I have not looked up the functions yet. But inv-t for, which would stand for inverse t, is the function you use in the TI-84 if your calculator supports it. You want to enter the area to the left that you're after and the degrees of freedom, and then it will spit out your value. So these are all one-tailed, because we were only looking at one tail, literally. Sometimes we're after areas on both sides, so we're looking at two-tailed distributions instead. So just like with the critical z-scores, we're after a t sub alpha over 2 instead of a z sub alpha over 2. So let's look at an example. If we have 7 degrees of freedom, and we know that the areas to the left and right combined are 0.02, so that means the area to the left is 0.01 and the area to the right is 0.01. We can look this up. We'll use the area in two tails. We end up with 2.998. I'll skip right to that. We're now looking at the area in two tails column, so it's 0.02. You'll note this does correspond to the column for 0.01, right? Because we're at 0.01 on each side, so it should be the same t value. So you should notice that the area in two tails confidence, sorry, not confidence. Well, it does correspond to confidence. The probability for the area in two tails is always exactly double the area in one tail portion. So we're after 0.02 or 0.01 on each tail, and 7 degrees of freedom is 2.998. If you're doing this with the calculator, you need to do that that calculation and only give it the area in one of the tails before you do it. I could, if I wanted, put in 0.02 divided by 2 here instead of 0.01. Probably no reason to do it that way, though. Okay. The other way we use two tails is if we're after the area that's outside of those tails, the area inside. So if we were, rather than looking at from the alpha equals 5% if we're looking at the confidence of 95%, and that's the perspective we need to use. We do have to do a little bit more manipulation to know which column to use. So in this case, we're going from negative alpha, t sub alpha over 2 to t sub alpha over 2, and we're interested in the area in between. So if that area we're after is 95%, we need to consider the area that remains in the tails. Easiest way to do this is to say, okay, we're after 95%, that's excluding 5%. I can find the critical t values associated with what's excluded, and that will be the same values. You see, so 5% remains in the two tails, so I could use the 0.05 two tails column or the 0.025 one tail column and find my critical values that way. So if I start with the start area in between, I can subtract that from 1 and use the one or two tails as appropriate to correspond. You may note that the tables only give some fairly small values. For the one area under one tail, I'm sorry, I keep saying table instead of tail. We've got a 0.005 and 0.1 as my range. So if I've got a 90%, I could subtract 1 from that, or subtract that from 1, and realize I need to look at the 0.1 column, and it should give me the same value. I'm just coming at it from the other direction. So if I was after 99% along this side, pretend it's a one tail for a minute, that would be the same thing as looking up the 1% value. So let's find the critical t value for a distribution with 29 degrees of freedom, such that it's two-tailed distribution, and we want the area in the center that's at 99%. So that area in the middle, that leaves 99%, that leaves 1% in two tails. So then I can go look at here, there's my 1% in two tails and 29 degrees of freedom, and I end up with 2.756. Okay, again, if we're doing this with the TI, we need to do that alpha over 2 calculation. With Excel, there's something else you do to tell it if you're looking at a one-tailed or two-tailed distribution, set up a little bit differently. But here you do that calculation on your own. All right. So next example. If we want to find the critical t value for a 95% confidence interval with 24 degrees of freedom, so let's see. So that 95, subtract that from 1, it's going to be 5%, half on each side, so it's going to be 2.5%, or 0.025, and 24 degrees of freedom, 0.025 for the calculator, or 0.05 on the areas with two tails table. Pause on that, so if their explanation makes more sense than mine. Here we go. So 5% here, which is the leftover portion that's outside of the area I'm after. But the boundaries between what I'm after and what I'm not after are the same no matter which direction I come at it from. 24 degrees of freedom, I get 2.064. There we go.